Thank you. Thank you all for being patient. Irony of the talk, I was about to talk about fault tolerant systems and low minimal latency systems, and there I am, already delayed. But I'll try and make up. So basically, I had few demos on my laptop, which were away from the code world, and it was actually code, and we were to run some real-time topologies. So please feel free to catch me after the talk, and I'll be happy to show you the demos. This is a HTML presentation, but it's screwed up because the laptop has IE. So I'll just scroll down, and so please bear with me for the time being. So the title of the talk is Designing Near Real-Time Processing Systems. I think the keynote and the talk we had before has already set the platform right. We've talked about IoT or IoE, which is like Internet of Everything and Internet of Things, which is producing humongous amount of data, variety of data, and at different frequencies. We've talked about Spark, which is like batch processing. We've talked about Spark streaming, which is like micro batch processing system. And now we're going to talk about Storm, which is like real-time processing system. So I think it would cover all the flavors that we're going to see throughout the 3 days over here. Why do we care? As I mentioned, we are generating data at a very rapid pace. Internet of Things, our applications. I've worked in environments wherein we've been generating data from how you surf on a website, how you surf on an application on a mobile device or tablets and stuff like that. And what was the first approach was simple. Dump everything to HDFS and then run MapReduce jobs on it and get insights. When we started to do that, it was a good starting point. And then the product guy said, hey, if we would have known this thing before, when the user generated this action, we would have done something to the application. All right, let's bring real time into the system. So what we decided to do was capture the moment when the data is being generated and then design the applications that read from your service layer and adapt to what the user is doing. For example, if I've already booked something on a website and then the next action would be to go to the home page or some other product catalog, my website should adapt knowing that this user has just already purchased something, not like tomorrow that user purchased something yesterday. So that's when I talk about near real-time systems and low latency systems. And so everybody knows about, I think, Lambda architecture. This is what it looks like on the paper, right? You have raw data, you have a streaming layer, you have a batch layer, and then you have a serving layer. Pretty cool. But this is how it actually becomes when you start to push that into production. So let's talk about it. Over here, you have some data sources generating lots of data. You have your web applications, your websites, which are generating clickstream data. You have your web server data, your application log data, and all that stuff. You have your traditional data systems like MySQL or Microsoft SQL and other stuff, and they're pumping a lot of data as well. And then you have these data ingestion systems, which I call, which are like Kafka, Logstash, or event aggregators. And then you have this near real-time layer. You will even have process data which you want to serve to layer, or intermediate results that you want to save for the time being, which I call this layer. And then you have your Hadoop layer wherein you're running all your jobs, right? Well, looks pretty much complex, and then you have your service layer. Yes, it is. Let's see what happens then. So let's summarize what I just showed above. So you have a data ingestion layer. Now, any streaming system you talk about is incapable without a good data ingestion layer. That's a fact, because any streaming system is not a storage system. So you don't have a storage layer after your streaming system, you need to have a storage layer after your streaming system, and you need to have a storage layer before your streaming system. So that's what I talk about data ingestion layer. Throughout the talk, I will cite examples wherein if there is a failover or there is a failure scenario in my streaming system, I would need a data ingestion layer to help me with that. Few examples are during my deployment strategies or during a lot of data, because the main challenge with streaming systems is the way my data inflows. My sources are unreliable, right? I don't know my sensors, when do they send me data, when do they stop sending me data, when is the influx there, or there are different frequencies. So these are some challenges that you would face designing your near real-time systems. Talking about processing layer, I've already mentioned these 3 patterns. These are the common patterns you have in your processing layer. Batch, very well, MapReduce jobs. You have microbatch, Spark streaming, an awesome solution. And then you have streaming layer, wherein you want minimal latency, like not even 500 milliseconds and stuff like that. That's where Apache Storm is going to talk about. And Apache Storm is not the only tool available in the market for that. There are other pretty much good open source tools for that, so you are free to evaluate them as well. Then storage layer. So storage layer, I treat them as three parts. One is your process data and your cooked data, which is like serving via dump cache layer. Then you have your persistent storage, where you ensure that all the raw data and your process layer is, which pretty much HDFS comprises of. And then you would have intermediate processing layer, which my stream processing logics talk to. Like some cache system like Redis or Cassandra is also a very good solution for that. Talking about stream processing layer, what are the challenges that I have? All the systems start with a worker and queue model. You will first put a worker, and then you will put a queue and process data, and then you will put another queue and another worker, and that's how you start scaling. But in all these things, these systems work pretty good. I'm happy. Even our systems used to work the same way. But what happens is, in this whole analogy of workers and queues, we tend to spend too much time building things around distributed systems, fault tolerance, guaranteed data processing, low latency, partitioning. And what I really forget is my business logic. That's what I'm about to focus on, my business logics. I need a framework that takes care of all these things, but I need to code my business logic. What I'll spend doing time is designing my distributed system and spending very little time on my business logics. But ultimately, you need a system wherein you can spend more time on writing business logics rather than worrying on the distributed computing system problems. Apache Storm is what it are the things that it highlights. Robustness. When I talk about robustness is like, if there is a failover, yes, there will be a failure in the Storm topology. It's not that there is going to be no failover in there. But how soon can I come back? Because it's a low latency system, you cannot have a downtime of 2 minutes, 3 minutes, or 5 minutes, right? You need to have insights in what's happening under the hood. For example, Storm comes with a very nice UI, which is like tells you what's happening, how many tasks, how many spouts have, how many streams have you emitted, how many acknowledged, how many not acknowledged, how many of them have failed, where is I need to increase the parallelism in terms of my bolts and stuff like that. We're going to talk all about that. Then partitioning, because it's a distributed system, when I flow my data out of my spouts, how does my data flow into my system? Which tasks receive what kind of data? All these things are already built into Storm, so you don't really need to worry about coding them by yourself. When I talk about stream processing system, there is a very fine line I like to draw, and that is like stream processing systems for me is a never-ending stream of job that is running. For example, a MapReduce job, even though it's a high latency job, it will finish executing at one point of time, right? But for me, stream processing job is a continuous running job. It will never finish. It will just keep on processing data and throwing out output. That's how it runs. If you even look at how a Storm topology works, it never stops. You really have to do a kill on the topology. That's how a Storm job stops, right? So it's an infrastructure where it will never stop. It will keep on running every time. Let's look at the components of what a Storm cluster is. At a conceptual level, you have three things: topologies, spouts, and bolts. And what flows into all of them is streams. Then at a physical level, you would have Nimbus, Zookeeper, Supervisor. I'll show you a pictorial representation of that. And then you have the executing components. That is what essentially runs on a node or a machine for me, right? So we talked about spout. So what is exactly a spout is? So treat spout as your interface to the outer world, right? It's your interface wherein your data starts to flow in your Storm topology. So for example, in this case, in all my slides, I'm going to showcase an example. It's from Wikipedia. So Wikipedia releases a real-time edit log. As people are editing Wikipedia, it releases data, right? So it's a very good data source to do any real-time stuff and stuff like that. And it's a JSON output. So the edit log looks like this. So you have something like action, what action was taken, what was the change size, and all of that. So I've built a topology basis this. So my spout is nothing. It's a WebSocket spout. What it means is it's reading something from WebSocket, right? That's all it's doing. So if you look at the code, what it's doing is it opens a connection with the WebSocket, and it starts to receive message. As it receives message, it just emits message, right? That's all it's doing. And then it creates a stream. So stream is an unordered set of tuples. It's not ordered. If you want ordered set of tuples, you would go into something like known as transactional topologies in Storm. But a simple topology in Storm is unordered set of tuples. And your bolts, which are the next component, you can have many bolts, so your bolts will start reading data from your spouts. Now, a bolt can read data from a spout, and it will have an output, and another bolt can read from a bolt or a spout. That's how your storm topology works. Now, I've been using this word topology quite often. What is exactly a topology? Topology is nothing. It's a stitched together network of spouts and bolts. That's what topology is. So if you look at this over here, what it says is, this topology says that I have a spout, WebSocket spout, which is basically reading from WebSocket spout. I have a parser bolt, which is nothing but a JSON parser. The input to this is my WebSocket spout. I'll talk about what shuffle means, and it is to run with a parallelism of 2. We'll talk about this. My spout runs with a parallelism of 1. My Redis bolt is nothing. It's just processing data that is coming from my counts bolt, which is my JSON parser bolt, and dumping the data into Redis. Now, this bolt is like the dead end of your topology. It's not emitting anything further. It's dumping everything to the Redis instance that I have. And then you just do sub sparse run and submit the topology name, which is Wikipedia logs. All these code examples that I'm showing you, so basically Apache Storm is 50% Clojure and 50% Java, and it has a very nice API which is known as the multi-lang API, right? So it does not stop if you're familiar with any other language to use that. For example, in my team, we were like mix of Java, Scala, and Python developers, and Apache Storm suited us really well because I could write in Python, someone else could write in Java, and we could even use components. For example, I have a topology that has a Java spout for Kafka, and rest of the bolts are in Python, right? And you can have vice versa as well. So I am currently using something known as stream parse, which is a Python library over Apache Storm, and all these code snippets are in that. The topology that I've written over here is basically a Clojure DSL that I've written. But if you are familiar with any other language, you are pretty comfortable with that. I mentioned about shuffling and random. If you see shuffle over here, so what this basically means. So Storm has something known as grouping. What is grouping is, now I have spout, which is running like at a parallelism of 3, and then I have a bolt, which is running at a parallelism of 2, right? Now when those 3 bolts start emitting something, which task does which message go, right? That is how you tell Storm that you want to do shuffling or you want to do grouping basis what. So when I say shuffle, so shuffle is basically a random grouping. So any task can receive any message. But if I want to maintain aggregates over one particular thing, for example, on Word, that all the words should go to this particular task, then I would use something known as word shuffling or field shuffling. So there are a lot of other shuffling fields available, shuffling methods available in Storm, which you can use depending on what kind of how you want to flow your messages inside different tasks, from one task to the other task. Primarily, I think most common ones used are the field shuffling and the group shuffling. But you have a couple of more. We talked about physical view. So there is something known as Nimbus, which coordinates via Zookeeper with the supervisors. Okay. Now, supervisor is something that runs on your each machine. Nimbus is something that you will have only one instance of. Nimbus does not currently work in a HA method, so you just need a one instance. And then Nimbus is basically, you submit your code to Nimbus, you upload a jar to Nimbus, and Nimbus ships it to all the supervisors. What else Nimbus does is Nimbus maintains which worker is up and down via the supervisor. So there is another layer ahead of supervisor, which is the worker, which I'll go next, but let's try and understand what's happening over here. So supervisor will run a lot of workers under it. Now, if one of my worker goes down, supervisor will just restart it, right? If my worker is continuously going down, this Nimbus will not receive a heartbeat message from the worker. Hence, it will shift all the stuff to a different worker, right? And fault tolerance is at every level. Nimbus and supervisors are a stateless daemons that are running on the machine because all the states are stored in the Zookeeper. So even if my Nimbus or my supervisor goes down, they are fail fast, they will restart them automatically. Or if it goes down and when they come back, because they don't have any state, they read their state from Zookeeper, so they'll be fine again. So you can even test this by simply doing a kill -9 on a Nimbus process to see what happens if it goes down. Other thing, if my Nimbus goes down, my Storm topology will not stop working. Why? Because Nimbus is just to monitor and to submit new code. So what will happen is, if my Nimbus is down and my Storm topology is running, if my worker is persistently failing, it will not be redirected to some other machine because my Nimbus is down. Or if I submit a new topology, that topology will not reach my cluster because the Nimbus is down. But your topology will still keep running. Similar thing, if my supervisor is down, your topology still keeps running. What will happen is my tasks will not be divided if my worker is going down. So in that case, it is pretty robust and it is fault tolerant. Inside supervisor, which is like a daemon running your system, is this. So this is what a worker process looks like. A worker process is part of your topology, right? A worker process runs executors, and an executor will run a task. So what you saw that I mentioned P1, P2, and P3. What does that mean? So that basically means that I have a parallelism of 2 and a parallelism of 3 or a parallelism 1. P is equal to the number of executors that I have, which are nothing just a thread that are running inside a worker. I can have multiple workers, and Storm takes care of deploying which worker will run which part of Spout or which part of my board. So for example, over here you have some yellow task and some green tasks. Both of them are running with parallelism of 2, so you can see 2 executors for them, right? So that is how Storm takes care of deploying your topology internally. There is a very nice read on the official documentation which says understanding the parallelism of Storm. So in case you're interested to know more how it's executing all that stuff, you should definitely go and have a look at that. Guaranteed message processing. This is one thing that is very important. When I have such influx of messages coming in, how do I guarantee that everything is getting processed, right? Now, Storm follows two paths. One is at least one processing, and the other one is exactly once. Now, at least once processing means that every tuple that flows in the system will get processed. True. At least once it will get processed. And the other one is, because you can have topologies in which you don't want a tuple to get processed twice, which means you want only exactly one semantics. So what Storm says is, yes, I will just have exactly one semantics, but it might get processed twice. So that's what comes under in the advanced features, which is known as transactional topology in Storm, which takes care of ensuring that your message might get processed twice, but you have a result which looks like exactly once. So that's why I differentiate between calling exactly once and exactly once semantics. In this part, I had to show you a demo of how things are working, how the Storm UI looks like, and how the Storm CLI looks like. But I'm sorry, it's not working right now, but we could have seen how it's working. Now, what happens is, you saw that there is Spout in which my incoming messages are coming, right? And then you have bolts. How do I ensure that if at any point of time, if my task dies or my bolt fails, how do I ensure that I don't lose messages? So what Storm does very beautifully is, when a message enters Spout, so we call it the Spout tuple, right? So let's consider a sentence that has entered Spout. So now a Spout tuple is that sentence. But when that Spout tuple goes to my different bolts, which can be, say, a word split or something, it will split that sentence into words, right? So now you started from a sentence, but now you have, say, that sentence had 5 words. So now my tuple is 1. But after that word split bolt, now I have the tuple count of 4 words and 1 sentence. So unless I finish processing on each and every tuple, the Storm will not consider it complete, right? So if any of the tuples fail, Storm will replay that message because one of the tuples failed. And how it does it is known as anchoring. So basically, it anchors each tuple with the root tuple of it. So it's like a tuple tree that it forms. And unless all the nodes in that tree are finished spending, it will not consider it complete. The other fallback to this is that you can set a timeout that the complete tree should process in n number of seconds. If it does not finish processing in n number of seconds, that I would fail the tuple again. That means it did not finish processing. So that's what is known as anchoring, and it comes with a reliability API in Storm. What can happen in this case is, my acknowledgement task die. So for acknowledgement, the block that we saw above, your acknowledgement will be a separate task altogether. irrespective of how many parallelisms you define, it will always same one acknowledgement task separately. And that you can configure that depending on the kind of topology you have, how many acknowledgement tasks do you want to have, 1, 2, or 3, right? So in case that acknowledgement tasks die, all the spouts that it was keeping track of will have to be replayed in Storm. Storm UI and CLI. So for example, I have parallelism running and all that stuff, and now I want to rebalance. Say now I see that my bolts are running out of capacity. I was running at a parallelism of 2. Now I want to increase my parallelism to say 4, or I want to run more instances of it. So Storm lets you do that from the CLI itself, which is called rebalancing. It is also an option that comes on the UI. So you can rebalance the number of executors that you have by just stating a number that this is my bolt and I want to run it with a new parallelism. You need not restart your topology in that case. So it's still running. Like I mentioned earlier, never-ending topology. So it's still running. You don't need to restart it, but you just scale it via the CLI. Coming back to other features, I mentioned trident topologies, which is like if you want, it's an analogy to how Spark streaming works, which is like micro batching. So trident helps you do micro batching inside. It starts batching tuples rather than flowing one tuple after the another. So it will batch tuples and then process them. And that's how you can figure out how to do exactly once processing and all that stuff. DRPC is, again, you want to execute a function on the fly in a distributed manner. That's how DRPC will help you. And so for example, we were using Kerberos authentication to make our Hadoop cluster secure. The similar options are available in Storm. So you can have your Storm topology, your Storm UI running behind simple authorization or Kerberos-like authentication. So you have a project for that as well. In case you want to use resource managers like Yarn or Mesos, Storm has projects which are running in production with Mesos and Yarn as well. So you can even leverage that stuff. When we talk about internal messaging, how my messages are flowing from Storm to other stuff, to other tasks, it's 3 categories. One is intra-worker processes, how my workers communicate with each other, then how my spout topology communicate with each other. There is no support. So you have one topology A, you have another topology B. Both topologies cannot talk to each other. You will have to use a digestion layer like Kafka or something in case you feel the need for both of them to talk to. Then deployment in these systems might become a bit tedious at first because you don't want to stop your topology, redeploy the other topology and test it. So there are scenarios, for example, we used to have the different instances of 2 topologies running, and then when we know that the new topology is working fine, we would stop the old topology. So depending on how you want to deploy, deployment might seem a bit tedious at first when you start with Storm. And Storm comes with a lot of parameters, configuration parameters, so you can scale at a Storm cluster level. You can set configuration across a cluster. You can set configurations for a particular topology. You can set configurations for a spout, for a bolt, and that's how configurable Storm is. Because it comes with a lot of configuration, so it's very difficult to measure the performance at first. So the best advice is to start tuning knobs one by one and then see what works for you best. There is no one set of configurations that will work for all topologies because each topology will tend to do different kind of work. So you will have to set the parameters basis that. And just like a topology, I can go on and on with this topic, but I think I'll put a stop over here. You can find me to discuss, have demos and stuff like that. I'll be here for another couple of days. Thank you. Questions?